we've got air moving. We talked about that last week. We talked about pressure. Uh, we've talked about temperature. There's one finer variable that we're dealing with, and that's humidity or moisture. So you are all interested if it's going to rain or snow at your house, I'm sure. So in order to understand that, we have to be able to understand how moisture moves in the atmosphere and what it, when the air becomes saturated or not saturated, how that all works. So this week we're going to talk about that some here. So how does the cycling of water in the atmosphere, maintains a habitable planet? Well, here's just a quick example of how moisture moves. You can see a plume of clouds all the way from central Pacific all the way into the west coast of the United States. This is called an atmospheric river. They happen all over the place, just happen to be fairly frequent out in the west coast sometimes in certain conditions. When they come in, they bring moisture literally, in this case, almost from Asia, all the way across the Atlantic and into the Pacific, into the west coast of the U.S. So other times you might see an atmospheric river coming out of the Caribbean into Texas or into the southern part of the United States. They're a very influential way that moisture moves. And think about it. If you're coming into the west coast of the United States, well, we know friction slows air down. So guess what? As the air is coming to the coast, it's beginning to slow. It's going to begin to converge, begin to lift. There's an initial mountain range very close to the coast of California, Oregon, Washington areas. So what happens is the air rises there. Some of it dumps a little bit of precip, but it doesn't necessarily rise as much as when it gets to the Sierra Nevadas. They're pretty high mountains. I was out there a couple of years ago, and yeah, I actually got over 10,000 feet on some of the mountain passes there, and I know they go higher than that. That air really rises up. It's pushed upwards when it hits it on these atmospheric rivers and dumps tremendous amount of precipitation. I have a cousin that lives in Lake Tahoe, and he has had over 10 feet of snow literally within a few days. So that is an atmospheric river really dumping a lot of precipitation. So let's look at this. Moisture moves all over the planet. Basically, it evaporates from some water source, like an ocean, lifts up into clouds, typically moving along, condenses, precipitation forms. Some of that precipitation comes back down into the ocean. So really no net change there. Other of that precipitation might come in and drop over land. Some of that land might be mountains, like in West Virginia. When I worked in West Virginia, there was a lot of precipitation sometimes on the mountains, and they would run into the lower valleys where the streams were coming down off the mountainside, causing pretty significant water rises on those streams. So sometimes the rain doesn't even occur on the part of the stream you live. I lost a friend in the Big Thompson Canyon flood a number of years ago, where the rain all occurred up at the upper top of the canyon near Estes Park, Colorado, ran down the canyon where they were camping. They didn't get a drop of rain, but the water in that river in Big Thompson Canyon literally went up 20 to 30 feet. And when it went up, it killed a number of people. And it turns out that people could have climbed up the sides instead of trying to drive out of it, but they chose to drive out. And that's where they died. Other parts, sometimes on land, you wind up in cities where all the water gets trapped and has to flow through artificial means, shall we say, of drainage, where all the land has been covered over with concrete or asphalt. And sometimes it just doesn't make it. Most times when you plan for developing a city and developing the sewer systems and stormwater drainage, they look at 100-year average rainfall. Every once in a while, we exceed that in thunderstorms. When we do, the towns and cities aren't equipped to handle it. Other times, you get flat land, like farmers might be farming their fields and all, and the water just settles nicely there and slowly sinks into the ground. So there are different phase changes that water goes through. Here you can see the list. We've talked about this in relation to how this transfers heat. It also transfers the state of water. Water is the only gas in the atmosphere that does change state. Humidity just describes the amount of water vapor in the air, and it varies literally from hour to hour, place to place. Summer typically has more humidity than winter. And here you have a whole list of how we as meteorologists measure moisture. And there is value to each one of these. We're just going to give you an introduction to them. So vapor pressure. All right, water vapor. It's a vapor. It's a gas, just like any other gas. So it has a pressure. And the higher that pressure is, the more water vapor is in the atmosphere. Typically, no more than 4% of the atmosphere's mass in the lowest kilometer is made up of water. And that is an extreme example. There are things called mixing ratio. What is that? It's the mass of water vapor per the mass of the remaining dry air. Okay, so think about it. I've got a cube of air, 1 foot by 1 foot by 1 foot. I look at it and I say, okay, this much is water vapor, that percent. And the rest of that cube is dry air. So I just lose a ratio of the amount of dry air, how many grams that is, compared to how many grams of the water vapor. That's mixing ratio. Specific humidity includes the water vapor. It's the only difference. So they're usually very close. Now, when air reaches its maximum humidity, in other words, it can't hold any more water, guess what? It can only hold so much water before it becomes saturated and it must condense. So when that happens, we just put a term saturated on every single one of these to indicate that these are air that can hold no more water. What disturbs that? The amount of water in the air? Heating of the air. Guess what? The hotter the air is, the more water it can hold. Why is that? Well, the energy and the molecules are moving them further apart, so the space for these water molecules increase in there. And they don't readily escape into actual water. They stay water vapor. Here's a chart. What I want you to notice here, and this is going to become really important in cloud formation and precipitation. We looked very closely here at liquid versus ice and the saturation pressure. Well, guess what? Saturation pressure is higher over liquids than it over ice. The reason being is the molecules move more in a liquid than they do in ice. They could be exactly the same temperature, but they actually move more in a liquid than ice. So that means that they have a better chance of going back into a liquid or into a gas when they're over liquid than they do over ice. So what that means is air pressure, water pressure actually, will tend to move always towards ice rather than liquid. So this is important. Next chapter. So most common measure is relative humidity. We think about it. Somebody told you, hey, the relative humidity is 100%. Wow, that's humid. Yeah, that can be humid, all right. But is that temperature outside air 32 degrees? Or is that temperature outside 90 degrees? The amount of water in the air is tremendously different between those two. So while this gives you a saturation and can help you pinpoint clouds or fog, it does not necessarily tell you how much water is actually in the air. All right, so we know that temperature influences how much water the air can hold. So as it gets colder at night, the air can hold less and less water. The relative humidity is going to go up. That's why fog forms at the end of the night, or sometime during the night. Because as the temperature is dropping, the air can't hold as much water, it condenses out. All right, and why does fog form in valleys? I mean, if you're in West Virginia or in a valley location in Ohio or Pennsylvania, what you'll find is the coldest air is the densest air. Where is it going to settle? It's going to settle in the valley. So that's why fog forms first in the valleys, then lifts up. Now, during the day, I want you to notice that the relative humidity sinks. Why does that happen? Well, the air is getting hotter, hold more moisture. So as the air gets hotter, the relative humidity goes down. Interestingly, we haven't really talked about evapotranspiration, plants. But plants actually release most of their moisture in the late afternoon and evening. So there's actually a peak. You can actually see a small rise in the relative humidity in the evening hours because of all the plants releasing moisture. Now, if you're in an area like a desert, that's not going to happen. But if you have a lot of plants, such as in the when the growing season's going on in the Midwest, corn plants, wheat, all of that contributes to it. Interestingly, they did a study in Oklahoma. When they harvested the wheat, they found out the amount of moisture in the air significantly went down. That was because the wheat, which was being irrigated and other things, was releasing that much moisture into the air to keep the moisture higher in the air. Once they harvested it, it went down. Dew point's another measure of moisture. A dew point is just a temperature that if I cooled the air, it's going to reach saturation. That's all it is. I made no change to the air. No change in pressure, no change in the amount of moisture. I just cooled it, and it reaches saturation 100%. So, like when you see in the morning dew on the ground or frost. Dew points change throughout the year. During the wintertime, they're fairly low. In the 20s, you can see like in Ohio, Pennsylvania. However, in the summer, notice the dew points rise into the 50s, 60s, and even 70s in some of the southern states. So, when the dew point reaches the same temperature as the actual temperature when they're combined, it's 100% relative humidity. The greater the difference, the further, the drier the air is. For example, today's a fairly humid day here at my house. Yet, temperatures started out in the upper 70s this morning, fairly moist, but the dew points were in the upper 70s. Relative humidity was near 100%. Now, just a couple hours later, we're already 90 degrees. The relative humidity's dropped back into the 70 to 60% range. So even though the amount of moisture didn't change in the air, the RH did. Now we're going to talk about stability. All right. You may not have thought about this, but have you ever seen a hot air balloon rise? And why do they rise in the air? Why does a balloon that's just been heated start lifting up and rising up? All right. We've talked about density. The big key is density. So if the air is less dense than the surrounding air, it's going to want to rise until it reaches the same density as the surrounding air. So we know air that is rising is cooling. How fast it's cooling depends on the amount of moisture in the air. So if I have an air parcel, look outside and see the size of a small cumulus cloud. We'll use that as an air parcel. At the ground level, the air has been heated. It gets warm enough that it is warmer than the air around it for some reason. That little section, maybe there's concrete, asphalt there, I don't know. But that gets very warm. That air is now going to rise up, and because it is warmer than everything around it, it's going to continue to rise. That air is going to cool, and it may cool faster than the air around it because the air around it's mixing out. So it winds up at some point being the same temperature as the air around it. It stops rising. But if in that rising process it manages to reach saturation, the temperature cools enough that the air water vapor begins to condense, guess what? It might rise a little further because now you're adding some heat into that air. It's not cooling as fast, so it might continue going up. And that is what we talk about when we talk about atmospheric stability. It adds another complication to how air rises. For example, unstable air is going to go up faster and faster. There's an acceleration there until it reaches the same temperature as the outside air. So we know that the air can cool at 9.8 degrees. Guess what? If you looked at an atmospheric sounding or temperature profile like a Stuvie diagram, you're almost never going to see air at 9.8 degrees on a lapse rate. Nor are you going to see it at 6 degrees. It's going to be somewhere between the two. So that's why these lifting processes allow the air, when it condenses, to continue rising. You all see in the desert necessarily clouds forming or whatever. The air rises because it gets very hot, but it cools very quickly as well when it's going up, so it doesn't rise as far. And there's an ascending branch of this air, and as the air gets colder, it's going to sink back down. So it literally creates a circular motion. Now, there are other things that might lift air. Warm fronts, cold fronts, mountain ranges, all of that can lift air. All of that can help air reach what they call the lifting condensation level, or the level at which the air becomes saturated. Mountains will cause a lot of precipitation to occur on the side the wind's blowing into, the windward side. On the leeward side, there's not as much moisture left in the air, so they don't get as much precipitation. And finally, we'll just talk about surface winds converging like on a sea breeze or a lake breeze in Lake Erie. So what I want to show you just quickly here too, to go along with this, is today dew points of moisture in the low levels on the east coast of the United States right now. I live in southeastern Virginia, and my dew points are in the mid-70s. Look to my south, dew points are in the upper 70s down here, even 79 degrees. Moisture coming up along the coast. There's a trough of low pressure. Notice the isobar dripping down here, sinking. So right in here somewhere, there's going to be thunderstorms, convergence today. And when that does, there'll be thunderstorms forming. Now, go out to Ohio. West of this cold front, look at the dew points are in the mid-60s. So there's a significant drop in dew point. Now, if I looked at relative humidity, your temperatures are in the 70s, my temperatures are in the 80s. The relative humidity could be close to the same. That's why you always got to watch relative humidity in terms you're dealing with. Finally, I just wanted to show you an atmospheric sounding, a Stuvie diagram here. And this is for Morehead City, North Carolina, this morning. Notice dew points are plotted on the left, temperatures are on the right. If I look at these temperatures, they look like, wow, it's really dropping off pretty quickly. Notice the dash lines, well, not the dash line, but the slanted line here. that is a dry adiabat. So if the temperature were to be along that line, that would be cooling at the same rate as if there was no moisture in the air. Now you'll see a curved line, a little harder to spot, like this one here. That's the moist adiabat. So it's not cooling as fast. Now those two things are what I'm looking for on a chart. So if I were to lift a parcel of air from down here at the surface along this moist adiabat, and I'm assuming it's going to be saturated because that's a very high relative humidity sounding there. So if it's saturated, it's going to move right along this moist adiabat all the way up to right about here where it hits it. So that air parcel's temperature is probably going to be slightly warmer all the way up to pretty high altitude. And in reality, that is what's called convective available potential energy. So there is some slight instability there today, already in the morning sounding. So this kind of thing we look at, the more instability, if that line was further over, like you get sometimes in the Midwest, when it's a severe weather event, the air will tend to fly up that much faster, let the clouds get that much higher. Stronger updrafts mean more potential for severe weather. In this case, there's a lot of potential for a lot of heavy rain and some pretty deep, big thunderstorms, but probably not a lot of severe weather. So hope you got a little bit out of this moisture stuff today. Let me know if you have any questions.